Hi, today we're going to discuss about inter-process communication with my team, Keerthi, Ramcharan, and myself, Krishna Chaitanya. Let's take an overview of what we're going to present today. We are going to give a brief introduction about inter-process communication, what is IPC and where it is actually used, and different system 5 IPC mechanisms like semaphores, shared memory, message queues, and also we'll discuss about signals. My teammate Keith will explain you about shared memory now.
Hi everyone, this is Keerthi. I'm going to talk about IPC mechanisms. In operating system, there'll be a lot of process running, and then sometimes they want to communicate with each other to, finish a specific task. Mhm. For this, there are three kinds of mechanisms we use. One is shared memory, message queues, and semaphores. And also, the process should have coordination among themselves. Um, they, the coordination should involve communication, synchronization, and mutual exclusion. Now, let's discuss about shared memory. Shared memory allows multiple processes to share virtual memory space. It is one of the fastest IPCs because the information in the shared memory can be accessed by all the processes immediately once it is available. Um, to create a shared memory segment, we use SHM get function. The syntax of SHM get has key, size, SHM flag as arguments. A shared memory will be associated with unique key when it is created. When we specify the key which already exists, the shared memory associates with that key will be used instead of creating a new one. For SHM flag, we give values like IPC create and IPC private. We use SHM attach if we want a process to be attached to the shared memory. If we want the process to be detached, we use SHM DT. SHM control performs the control operation specified by command on the system V shared memory segment, whose identifier is given in SHM ID. Semaphore is nothing but an object of tokens which is managed by the kernel. There are two types of semaphores, counting semaphore and then binary semaphore. If we have n resources, each token will be allocated to one resource in counting semaphores. An example for producer-consumer problem is beating barber. In the same way for binary semaphores, when a process writes some data into a shared memory, it will notify another process to read by sending notification token using semaphore. Proper validation must be applied to avoid deadlocks and logical errors. The semaphore concept can be used for synchronization and mutual exclusion between processes.
Hi, I'm Ramcharan. I'm here to explain about message queues, which is another mechanisms of System 5 IPC. Message queues are nothing but a vector of a buffer. These vectors are managed by the kernel. Communication between process happens through exchange of messages. Hence, the basic unit of exchange through message queue is a message. Message queues is just like a UDP in networks, which is a connectionless protocol. That is, message queues offer message-oriented connectionless communication between processes. That means messages can be sent to message queues even if no other process is waiting for messages. Every IPC mechanism has one thing in common. Whenever they are created, a unique key is assigned to them. Based on the key, a process can create a new message queue or it can connect to an existing one. And when you create a message queue, it won't go away until you destroy it. Some may get doubt, why can't we use read or write system calls for communication? The reason is the System 5 RPC objects are not integrated with input-output system. Hence, we cannot use the standard read and write system calls on the System 5 IPC objects. For this purpose, System 5 IPC message queues offers a set of functions for creating, communicating, and to perform control operations. Before a process can send or receive a message, the queue must be created using message get. The operations to send and receive messages performed by message send and message receive. And then message control performs control operations specified by the command on system 5 message queue with identifier message queue ID. Now we will see how this message queue works through a diagram. A process creates a message queue using message get, and a process will send the message to the message queue using message send. And if a process wants to read the messages, it will use message receive command. And if a process wants to control the message queue, it will operate through message control. Now let's see about the advantages and disadvantages of message queues. Firstly, with advantages. Communication in message queues can be driven by events. Application can assign a priority to a message. Hence, there is a security, data integrity, and recovery support. Now coming to the disadvantages. They are one-to-one in nature. Here, a queue is not a broadcast mechanism. So, when one recipient receives the message, it is no longer available for others to pick up. Sometimes, they create an additional operational complexity.
Hi, this is Chaitanya. My teammates have explained about System 5 IPC mechanisms. I'm going to explain about signals, which are considered as a limited form of IPC. So, what is a signal? A signal is nothing but an asynchronous event which actually delivered by kernel to a process. So, what actually signals are used for? I mean, what's the reason? What is the usage of signals? So, how can we categorize signals? Signals are actually categorized in two different ways. The usage. Signals are used for event notification and also for process communication. The signals which are used for the event communication are called as general purpose signals or standard signals, whereas the signals used for the process communication are called as real-time signals. In each of the notification, the signals used for notification and the signals used for the process communication consists of 31 different types of signals. So let's see what are those signals. We'll go with general purpose signals. Mostly signals are used for event notification. Let's take a look of it. So here is the list of the signals, general purpose signals. General purpose signals are usually referred with pre-assigned names. You can see here every signal is prefix of SIG, SIG. Okay, so every signal have its value and a default action. So let us suppose this particular signal has a value of 1 and this default action is to terminate. Whenever this signal is received, the default action will be taken will be the termination. Okay, and name of the signal is generally the event which it is mapped. For example, let's take a signal 6 segue. You might have came across when you are actually writing any C program and any segmentation violation occurs. A signal is reported. You will get a segmentation fault, right? That is nothing but a signal has raised because you have tried to access an invalid memory. So what happens mostly that the time the signal is raised, the default action will be terminate and dump the core. There are also signals used for asynchronous I/O like SIG URG, SIG IO, and SIG poll. And there are also timer signals called SIG prof, which is actually used for the optimization. Generally, a tool called gprof uses this particular signal, SIG prof. And signals are also used for error reporting. So these are the different list of signals. Now let's see what command we use to send a signal. In Linux or Unix-like systems, we use kill and values which have specified ESC. You can see the values here. the value kill hyphen value and the process ID. You don't just don't get confused with the name kill. This doesn't mean that you should use only to kill a process. Kill means to send a signal. It's a better, they could have renamed it in another way, but kill means to send a signal. So let us take an example. Okay, so let's assume we have a process ID 8976. We have to kill that particular process because suppose it might be got hung and want to kill that process. You can give a command kill -9. What is the -9 here? -9, the value of -9 is sig kill. So you are actually asking the kernel to kill this particular process ID. So when you give, you can the process get killed. You can check with the command ps. All right. How internally signals work? How they get generated? How they get delivered to the destination process? One thing is signals can be sent only to a process. Okay, and signal delivery is done by a process manager of kernel, which is known as signal subsystem. So there are three entities by which a signal can be generated. They are process, exception handler, and kernel services. Let's have a look how actually the internal things goes in the signal. Let's suppose, like just now we discussed that the source of generating a signal can be a exceptional handler, a process, or a kernel services. These are the sources where a signal gets generated, and these signals sent to the signal subsystem, which delivers to the destination process. This is how actually the generation and delivery of the signals happens. And signal generation and signal delivery need not be a continuous occurrence. Means once, as soon as you generate a signal, the delivery to the destination process doesn't happen immediately. There may be a delay. Let's see why it gets delayed between generation and actual delivery of the signal. So signal delivery is lost when the destination process does any one of the following. The destination process is currently handling previous instance of the same signal. Destination process is in uninterruptible wait state when the destination process has explicitly disabled signal handling. When any one of this is true, the signal delivery will be lost. So what happens? What about the undelivered signal? Undelivered signal will be queued in the receiver process pending list. So this is about general purpose signal. What about real-time signals? Real-time signals are queued in the PCBs, process control blocks real-time signal list, and they are never lost. That's the benefit of real-time signals. They will never get lost. So now we have delivered the signal. So some process has received it. Process is nothing but applications, right? So how the application will respond on the reception of the signal, how the application will respond, we'll see. They will respond by any one of the following. They will execute the kernel defined signal handler. What do you mean by that? Execution of kernel defined signal is nothing but the default action taken by the kernel when this particular signal arrives is to dump the core, or is this particular profile signal arrives to terminate the process. So that is the kernel defined signal handler. Or what may be other scenarios? Execution of application defined signal handler. What do you mean by application defined signal handler? We can write our own signal handler. Instead of a default action which is handled by the kernel, we can write our own signal handle function. Suppose one particular signal is received, instead of doing its default action, perform different action. And another scenario will be we can just ignore the signal. But remember that two signals you cannot change. Two signals like sig kill and sig stop cannot be caught, blocked, or ignored. What do you mean by that? You cannot change the default behavior of them. I mean, you cannot rewrite your own application defined signal handler for these two signals. It's always preferable to go through the manual pages of signal. You'll find lots of signal types here and their usage and why they are used. Signals are actually POSIX standards, so you can find we can find the updates about recently added signals as well. Any changes can be shown in the manual page. Thanks a lot for watching this video.